Hello and welcome to the S-Chemistry lecture series. In this video, we're going to look at section 2 of chapter 15, and we're going to start to look at the reactions of alkanes. So we're going to see now not just what are alkanes and where do they come from, but how do they react? What chemicals do they react with, under what conditions, what do we observe, so on and so forth. Now, the reactivity of alkanes is a pretty straightforward topic. Alkanes consist, as we saw earlier, of only single-bonded carbon to hydrogen. It's all CH and CC bonds. Both the carbon-hydrogen and carbon-carbon bonds are non-polar in nature. Carbon and carbon have the exact same electronegativity, the same element, and carbon and hydrogen have a very similar electronegativity, with carbon being 2.2 and hydrogen being 2.0. So the difference is only 0.2, making them a non-polar bond. Because the whole compound in alkanes is made out of these bonds, then the whole molecule is non-polar, sorry. So because the whole molecule is nonpolar, it makes it really hard to react an alkane. Because there's no partial negatives and partial positives, the electron density of alkanes is very evenly distributed. Now, when we talk about the term electron density, we are talking about the locations where electrons are. So we're talking about either positive density or negative density. A molecule that's polar would have an area of high negative density and an area of high positive density, because it will have a negative pole and a positive pole. But things that are non-polar have a very evenly distributed electron density, and so there are not areas that are positive or negative. They're very non-polar all throughout. So because of this, they do not attract, and to use some of the words we learned earlier in chapter 14, they don't attract electrophiles or nucleophiles. There's no positive to be attracting any nucleophiles, because remember, nucleo meaning attracted to positive, and there is no negative to attract electrophiles, because remember, electro meaning negative, so it's electrophiles attracted to negative charges. Because of this, alkanes are going to be extremely unreactive. Alkanes are amongst the most unreactive organic compounds in all of organic chemistry because of their non-polarity. So they can only really undergo two chemical reactions, which are very extreme reactions. The first is combustion, which we're going to look at and everyone should be familiar with. So we're going to look at combustion, but not just in the light of organic chemistry. We're also going to look at combustion in the light of environmental sciences and what exactly burning of fossil fuels causes, which we visited already in chapter 13. And then we are going to look at a much more complex reaction, which is our first really full organic reaction, which is free radical substitution, which is going to happen with halogens and alkanes in sunlight. So these are going to be kind of the two sections to our chapter 15, section 2. We're going to first look at combustion, and then we're going to look at free radical substitution reactions. Now, before we get into this, though, there is some nuances of organic reactions that we need to talk about. So every time there's a slide with a chemical reaction that you need to remember in organic chemistry, we're going to have this little key at the very top right of our slideshow here. What is this key going to do? Well, as these slides go through, we're going to see slides where chemical reactions that need to be memorized are presented, and the different parts of the reaction is going to be presented in different ways. Any chemical that acts as a reactant in that reaction will be underlined. And I don't think I need to explain that too much. We all know what a reactant is. So these are the chemicals that you need in order for the reaction to happen that are actually reacting with each other. A lot of the time, these reactants are going to be organic compounds, although you might have some inorganic compounds as well. Any compound that is in bold, or any chemical that is in bold in the slide, is going to be a product. And this is what the end result of the reaction is going to be. What are the chemicals that are the end result? Again, a lot of the time, these products are going to be organic, because in organic chemistry, we mostly care about what happens to the organic compound. And this is something I already brought up in chapter 14, but organic chemistry is very organic compound centered. And so a lot of the time these reactants and products, although they can be inorganic, will mostly be organic compounds. Now, one of the best ways to look at organic reactions is to see them as one functional group becoming another. So functional group A becomes functional group B. This is the best way in which to look at organic reactions. Organic reactions are all about changing the functional groups. So whereas the reactants that are underlined will be one functional group, the products will be a different one. For example, we could change an alcohol into a halogen alkane, or an alkane into a halogen alkane, or alcohol into an aldehyde, so on and so forth. So always view these reactants and products as functional group A becoming functional group B in the products. So always be on the lookout for how what the reactants are, which functional group, and what the product is of that reaction, what type of functional group it is. But then, apart from reactants and products, which are very standard for chemical reactions, there are three other things we need to be in the lookout for when it comes to organic reactions. The first is a double underline, which is going to symbolize conditions. What are conditions? Conditions are what else is needed outside of those chemical reactants. So anything that's not a chemical, things like a temperature, is it cold, is it hot, does it need reflux, and we'll discuss what reflux is later on. Is it a high pressure, is it a low pressure? Is there a specific solvent? So maybe the chemicals, the reactants cannot be in water, maybe they need to be in ether, or they need to be in ethanol instead of water, and they're not aqueous. So that's what we will classify under conditions. What are the conditions, the non-chemicals, solvents, temperature, pressure that is needed? And those are always going to have a double underline in the slide. A dashed line underneath a word is going to be an observation. Observations which you will be asked for in the AICE exam are what do we see? What do we visually observe when this reaction happens? Does it start bubbling? Is there a color change? Maybe the solution turns from clear to brown, or from orange to clear. Is there a colored precipitate? So anytime we have a precipitate, remember, precipitate is a solid created from aqueous solutions. Is there a color precipitate? Is there a blue precipitate or a white precipitate? Be specific. So what do we see? Those are observations, or they're going to be with a dashed line underneath them. And then finally, something we might need is also a catalyst. Some organic reactions have a catalyst associated with them, and usually those reactions won't happen without that catalyst. So maybe a reaction needs zinc or palladium as a catalyst. That reaction in organic chemistry will usually not occur unless that catalyst is present. And anytime there's a catalyst that coincides with a reaction that is needed, that catalyst will have a dotted line underneath. All right. So this little key will be at the top right of any slide where you need to memorize a reaction. That way we can always reference it as we go through the reaction. The one thing that is not on here that you might still need for some reactions are their mechanisms. And again, we talked about how the mechanism is how the reaction happens. And you will need to memorize some very specific mechanisms for very specific reactions. But those aren't on the key because those will be very obvious. I will literally spend a few slides usually on a single mechanism for a reaction. You do not need to know the mechanism of every reaction, but there are key reactions you need to know the mechanism for, and we will point those out and we'll go through them. All right. So let's start with our first reaction of organic chemistry, which is combustion. Now, not the most exciting reaction, but a reaction that is a good segue into organic chemistry because we are all have a basic understanding. We're basically familiar with combustion, right? Alkanes can undergo combustion reactions like most organic compounds. They get oxidized by the air, the oxygen in the air, to different degrees because oxygen in our Earth is available everywhere, right? It's in the air that we breathe. It's only 1% of the air. So alkanes are going to undergo combustion reactions by reacting with the oxygen in the air. But they can do it to different degrees. So what we have learned so far, up to now, we are used to seeing, is what we call a complete combustion. A complete combustion is going to happen when an alkane, like C8H18, reacts with excess oxygen. And what happens is that the oxygen acts like an oxidizing agent, oxidizes the alkane, and the products are going to be carbon dioxide and water. That is what called a complete combustion. Why complete? Because we have an excess of oxygen with complete combustion. Meaning that there is so much oxygen in the air, or there's so much oxygen present that every single carbon can be completely oxidized. Every single hydrogen can be completely oxidized. Now, a few things to point out here. Notice how excess is in double underline. That's because it's a condition. It's not just that we have oxygen, it's not just that we have O2 as a reactant and the alkane. We need that O2 to be in excess, meaning that we have more oxygen than we need. And this is important here. Why? This is important because there's also what we call incomplete combustion, which we are less familiar with. When oxygen is limited, we do not undergo complete combustion. We undergo incomplete combustion. With limited oxygen, not every carbon and hydrogen can be fully oxidized. So what happens? Alkanes, which are single underline because they're reactants, will oxidize only partially, and instead of forming carbon dioxide and water, they'll form carbon monoxide and water. Why is this called incomplete combustion? Because the carbon monoxide means that the carbons have not been oxidized as fully as they have with complete combustion. They form CO instead of CO2. Less oxygens, therefore less oxidized. So with that small change in conditions, with the oxygen being limited instead of in excess, we actually get a different product, which is the carbon monoxide instead of the carbon dioxide. All right. So that changes your balancing, of course, that changes the product. So you gotta be careful with organic chemistry. Small change, one word, excess versus limited, is going to change the type of reaction that happens. So complete combustion, that's usually when we see the blue color flame in our Bunsen burners, that's complete combustion. Whereas an incomplete combustion will lead to a more orange flame because of that carbon monoxide being created. Incomplete combustion does not usually happen in open air because there's plenty of oxygen. It often happens in car engines and other type of internal combustion engines because engines don't necessarily have a lot of oxygen in them. We rely on an air intake for engines, and the area and space where combustion happens is limited. So a lot of the time that combustion is incomplete and it creates carbon monoxide. So let's dive into that because this is going to come into what we are going to segue essentially into our environmental science portion. Again, environmental science, but with a very chemistry lens. So why are burning fossil fuels dangerous? We talked about this in our chapter 13 when we were talking about nitrogen, but we focus a lot on the effects nitrogen has. So let's talk about other pollutants like carbon monoxide. Carbon monoxide, which is created through the incomplete combustion of alkanes in fossil fuels, like gasoline having octane, can lead to a lot of issues. Mainly that carbon monoxide binds to hemoglobin in the blood of people, and it deprives us of oxygen. Hemoglobin, and this is a very basic graphic here, but we don't need the specifics of the biochemistry. Hemoglobin is the part of your blood that binds oxygen and moves it around. Carbon monoxide and oxygen are very similar in size. Oxygen is made of two oxygens, atoms, whereas carbon monoxide is made of an oxygen and a carbon. That carbon is very similar in size to the oxygen in O2. And so carbon monoxide can actually very easily take the place of oxygen in blood. And so it deprives your blood from being oxygenated. It deprives your body of the oxygen that it needs to function. Since carbon monoxide is odorless, we can smell it. And the only real side effect that it has is dizziness because of the lack of oxygen. It's extremely dangerous because by the time people realize what's going on, it's often too late. It happens a lot in Miami, where we live, that people have their generators inside after a hurricane, and generators are essentially engines. They create carbon monoxide, and so they run them inside, house fills with carbon monoxide, and people are die and or end up in the hospital because of it. Many deaths are due to this carbon monoxide poisoning when you use generators in rooms that are not well ventilated. So that's one of the downsides of carbon monoxide and burning fossil fuels, and that's a human side of it. To the environment also, carbon monoxide contributes to climate change. It acts like a greenhouse gas, just like carbon dioxide, and it traps heat into our atmosphere. Carbon dioxide, though, is a bigger greenhouse gas than carbon monoxide. So even if the combustion in burning fossil fuels is complete, it still creates a carbon dioxide, which creates a greenhouse gas effect and contributes to what we call enhanced climate change. Enhanced meaning that it's happening a lot faster than it should be. So, what are some other dangers? We already discussed this, so I'm going to go over this briefly. But some other dangers of burning fossil fuels are the creation of nitrogen monoxide and nitrogen dioxide, which we discussed in the nitrogen chapter 13. In normal combustion, the nitrogen gas that's in the air is not oxidized because it has a very high bond energy, like we talked about in chapter 13. However, car engines get so hot that nitrogen, because of the heat, can be oxidized into nitrogen monoxide. That nitrogen monoxide then gets further oxidized in the air to nitrogen dioxide. And those nitrogen monoxide and dioxides have a lot of side effects for the environment, which we've discussed already. Like they contribute to acid rain by reacting with water and creating nitric acid. So nitrogen dioxide can react with water in the atmosphere in rain clouds and the oxygen in the air, and it creates nitric acid, HNO3. The nitric acid, along with sulfuric acid, which we'll discuss in a second, then falls down and creates acid rain. A small amount of nitric acid is normal in the atmosphere and in the rain, but it is in very high concentrations in acid rain. The nitrogen dioxides and monoxides can also act as a catalyst in the oxidation of SO2 into SO3, creating sulfuric acid. Sulfur dioxide, also made from the burning of fossil fuels, because some fossil fuels have sulfur in them. Usually they're sulfur contaminants, impurities. When that sulfur is burned in the fossil fuel, it creates sulfur dioxide. Along with the nitrogen dioxide that's created, That nitrogen dioxide can react with the sulfur dioxide to create sulfur trioxide and the nitrogen monoxide that is also a byproduct. But the nitrogen monoxide can actually react with oxygen to recreate nitrogen dioxide. That's why we call this a catalyst, right? It's not a true catalyst in the sense that this happens in the same reaction, but the nitrogen monoxide that gets created can recreate the nitrogen dioxide, so it goes back and does the same reaction. So it is a form of catalyst in the sense that it creates a cycle, a reusable cycle of nitrogen dioxide and monoxide. The sulfur trioxide, though, that gets created during this reaction, then can react with water in the atmosphere, again, rainwater, and create sulfuric acid that rains down as acid rain. So again, we had seen this in the chapter 13, but because we are studying fossil fuels and their burning, it is an important topic to revisit. Another topic that we have discussed, and it's important to revisit, and a much greater depth, is the creation of unburned hydrocarbons. So another part or another issue with internal combustion engines is that they are not 100% effective. Internal combustion engines, when they burn gasoline, some of that gasoline, some of those hydrocarbons go unburned, meaning that they're released into the atmosphere. And we call those volatile organic compounds, or VOCs, which we discussed in chapter 13. Some of those compounds are carcinogenics. They can get into our lungs, into our cells, into our DNA, and they can cause different forms of cancer, like lung cancer, lymphoma, stuff like that. So they are carcinogenic, these unburned hydrocarbons that go into the air. Other unburned hydrocarbons, or volatile organic compounds, VOCs, can also form PANs by reacting with nitrogen oxides in the air. And those PANs are what contribute to what we call photochemical smog, that we more normally relate to pollution in the air. That hazy look that we get over cities like LA and Mexico City, which sit inside of basins and valleys. So the creation of PANs is another issue that comes from the burning of fossil fuels and hydrocarbons. So how do we treat this? Something that we saw in chapter 13 was the use of catalytic converters. Now we're going to study this a little more in depth than we in chapter 13, because it does deal with alkane reactions. The exosystems nowadays are fitted with what we call catalytic converters. They're this piece of your exhaust where inside there's this honeycomb mesh made out of catalytic metals that act like catalysts for specific reactions. These are precious metals, things like rhodium and palladium, platinum, stuff like that. So these precious metals act like catalysts for three major reactions. The first is the oxidation of carbon monoxide to carbon dioxide. So some of these precious metals are going to speed up the conversion of CO, carbon monoxide, that is the result of incomplete combustion, with oxygen to create carbon dioxide. So that is going to cancel out or to eliminate one source of our pollution of carbon monoxide. So by using catalytic converters, we get rid of carbon monoxide through this reaction. We also speed up the reduction of nitrogen oxides to nitrogen gas by carbon monoxide. So another kind of two-in-one reaction is that carbon monoxide and nitrogen monoxide can actually react with each other. And one of the catalysts in the catalytic converter is going to speed up this reaction, which creates carbon dioxide and nitrogen gas, which is very harmless. It's in the air already. It makes up like 70% of the air. So this reaction being sped up gets rid of carbon monoxide and nitrogen monoxide, two very big pollutants from burning fossil fuels. Finally, that oxidation, the oxidation of the unburnt hydrocarbons that we talked about, the VOCs, also gets catalyzed here, and it creates carbon dioxide and water. So essentially, all those unburned hydrocarbons, those CnH2n+2, because it can be a lot of different hydrocarbons, reacting with oxygen, this is going to get sped up to create carbon dioxide and water. Again, this gets rid of another pollutant, which is the unburned hydrocarbons. So the catalytic converter takes care of three big pollutants in fossil fuel burning: carbon monoxide, nitrogen monoxide, and unburnt hydrocarbons. The problem is, though, they all create carbon dioxide, which, as we know, is a greenhouse gas. It traps heat into our atmosphere, contributing to enhanced climate change. So essentially what catalytic converters do is that they trade three problems for one. They trade carbon monoxide, nitrogen monoxide, and unburned hydrocarbons for one big problem, which is a greenhouse gas, which is carbon dioxide. So it reduces the number of toxic gases released by cars. It does not eliminate the production of carbon dioxide. In fact, it actually makes more carbon dioxide. But now we just need to treat the one problem, which is the creation of carbon monoxide. So that's it for this first section of chapter 15.2. That's what we're going to talk about. That's all we're going to talk about with the combustion of alkanes, right? We're talking the burning of them, the different types of combustion, incomplete and complete, and the different effects that it has in the environment. Next up, we're going to talk about the second reaction, which is free radical substitution. So this is the other reaction that alkanes can undergo. Like we said, alkanes are very unreactive. They are non-metal, they're non-polar, right? Because of the carbon-hydrogen bonds and the carbon-carbon bonds. So they can only do two reactions. Combustion is one. Free radical substitution is the other one. So let's break down, before we actually go into what it is, let's break down the term so far. So remember that substitution means the replacement of a functional group. So we're going to be replacing a functional group. Well, this is an alkane. So we're going to be replacing the hydrogen for something. And then free radicals, if we remember from chapter 14, are compounds with unpaired electrons. So these are going to be very reactive compounds with unpaired electrons that are the result of homolytic fission. So just from reading the title, free radical substitution, we know something, probably the hydrogen, because the only thing that you can replace in an alkane is going to be replaced. And because it's free radical, it's going to be replaced by a free radical that's a result of homolytic fission. Now, what exactly is free radical substitution? Free radical substitution is when an alkane, and again underline because it's a reactant, is going to react with a halogen in sunlight to undergo a substitution reaction. So here we have our two reactants, which are an alkane is reacting with a halogen. So alkanes react with a halogen. And there is a specific condition here. Notice how that that sunlight is double underlined. Because if it's a single underline like alkanes and halogens, then that is a reactant. But the double underline in sunlight means that it is a condition. So this reaction only happens if we have sunlight. If we have, more specifically, ultraviolet light. Because that's really what sunlight is. Anytime we say sunlight in chemistry, we mean UV radiation. Ultraviolet light. So in this reaction, what's going to happen is that the hydrogen, or one or multiple of the hydrogens in the alkane, is going to get substituted by a halogen, leading to the creation of a halogenoalkane and hydrogen halides. So notice these are bolded here because, again, the key here says that if something's bolded, it's a product. So what are our products? Halogenoalkanes, and no, it's not a specific reactant because our product, because that's our, depending on which alkane we have, and a hydrogen halide. Those are our two products. So what do free radical substitution reactions essentially look like? An alkane reacts with a halogen to create a halogenoalkane and a hydrogen halide. So something like C2H6, which is ethane, could react with Cl2, chlorine, under ultraviolet radiation, because we need sunlight, to create something like chloroethane and hydrogen chloride. This is our alkane. No, let me use a different color. This will be our alkane becoming a halogenoalkane. So this is one of the reactions we can use to convert an alkane into a halogenoalkane. I mentioned earlier to always view organic reactions as a functional group becoming a different functional group. So free radical substitution specifically is how alkanes become halogenoalkanes, or one of the ways that this can happen. So how exactly does this reaction happen? Because I mentioned that for some reactions, you will need to know the mechanism. Not just how and where, not just what and where. So not just that an alkane becomes a halogenoalkane with the help of a halogen and also creating a hydrogen halide, but how does this happen? Well, this reaction is going to occur through a three-step mechanism that includes the creation of a free radical. So one of the things that we can get from this word up here, the name, is that substitution is the type of reaction. So substitution here is the type of reaction, whereas free radical is the mechanism of the reaction. So this is a substitution reaction that happens through a free radical mechanism. And like we mentioned in chapter 14, free radical mechanisms are always going to occur in three steps: the initiation step, the propagation step, and the termination step. We reviewed this very briefly in chapter 14. We are now going to look very closely at what this mechanism is. So I'm going to do that over the next couple slides, but before we get into that, one of the things that you should be realizing here is that the free radical substitution reaction can actually get rid of halogens. So this is going to be one of those areas where we can actually overlap inorganic and organic chemistry. Why? When this reaction happens, the concentration of the halogen goes down. So imagine we had a reaction between hexane, C6H14, and bromine, which is Br2. This will be a free radical substitution reaction. Well, if we mix these two and we leave them in a dark place, nothing happens. We get no reaction. That solution, because bromine is an orange liquid and hexane is colorless, we will mix them together, nothing will happen, and we will get no reaction, which will be accompanied by a visual of the orange liquid staying orange. Because we know bromine from chapter, I think it's 12, we know bromine is an orange liquid, orange-red liquid. And a bromine water, when it's aqueous, an orange solution. We also know when it's mixed with hexane, it turns very brightly orange. So if we do this in the dark, nothing happens. Whereas if we do this in the presence of sunlight, these two would react with each other to create some form of halogenoalkane and HBr. Well, that means that the concentration of bromine is going to decrease. So what do you think is going to happen to that orange liquid or an orange color of bromine? It's going to disappear. So this is the reaction. If we mix these two in the dark, nothing happens and they remains orange. But if we mix them in sunlight, we get rid of that orange color of the bromohexanes. Bromohexanes are actually colorless, and so that color disappears. This is a mixture of the organic and inorganic concepts, and it's something that you should eventually be able to do and ration out as you learn more and more chemistry. But it is a critical thinking situation or a critical thinking scenario. Understanding that when hexane and bromine are mixed, if the right conditions are present, they will react. And those right conditions are sunlight. Meaning if we do this, mix this in the dark, nothing happens. We keep the orange color. But if we do it in sunlight, they actually react with each other. They create bromohexanes and hydrogen bromide, both of which are colorless, so the reaction or the color disappears. This is what I mean by observations that you could be asked about. So, coming back from that detour, let's talk about the mechanism for free radical substitution. The mechanisms for free radical substitution happen in 3 steps. Now, going back and let's review a little bit of what is a mechanism before we go straight into this one. A few things to remember when we're dealing with mechanisms. A mechanism describes how the reaction happens by showing the movement of electrons. So not just that the alkane and the halogen react to create the halogen alkane and the hydrogen halide, like HCl or HBr, but how does that process happen? A mechanism can occur in one step or multiple steps. In the case of the one we're about to see, the free radical substitution mechanism happens in 3 steps. The movement of electrons is going to be shown by a curved arrow. The arrow must be curved and it must start at a lone pair of electrons or a bond because it's showing the movement of electrons. Meaning that beginning, that tail of the arrow, has to either start at a lone pair or at a bond, like here and here. An arrow with a full head, if we remember, is going to represent the movement of 2 electrons. So here we will have 2 electrons going from the bond to this chlorine. Whereas if it has a half head, it represents the movement of 1 electron. Meaning like here, where this bond is being broken and 1 electron is going to this chlorine and 1 is going to this chlorine. So also, if you remember, this right here is homolytic fission. Because the bond is being broken evenly, that's where the word homo comes from, 1 electron to each, whereas this is heterolytic fission. The word hetero meaning unevenly, meaning that both of the electrons are going to just 1 chlorine. This is bond creation, not fission. This is when a bond is being formed. So that's not fission. Fission means breaking a bond. So, now that we reviewed that real quickly from chapter 14, let's jump into free radical substitution's mechanism. So like I said, there are 3 steps to free radical substitution. Now, one of the things I will say about these 3 steps is that a lot of the issues that come with understanding free radical substitution is that a lot of people see these steps as being sequential, meaning they think step 1 is going to happen, and then it's going to stop happening, and step 2 is going to happen, and then step 2 is going to stop happening, and then step 3 is going to happen. This is not true. Free radical substitution mechanism is not sequential. What it is that some of the molecules in the mixture, so let's make a little container here. I'm going to make a beaker, but it's not really a beaker. Some of the molecules in this mechanism might be undergoing step 1, while other molecules in this beaker might be undergoing step 2. And then a different subset of molecules in this beaker are going to be undergoing step 3. Meaning that the 3 steps are not sequential in the sense that they are not going to be happening one, then the next without them connecting or without one finishes. But what's going to happen is that they're going to feed into each other. Step 1 creates things that feed into step 2. But while step 2 is happening, step 1 is still happening to other molecules. Step 2 creates molecules that feed into itself, because step 2 is a chain reaction like we mentioned before, but it's also going to create molecules that feed into step 3, which is the determination step or the ends. So all of these are happening at the same time. While some molecules might be undergoing step 1, others in the exact same beaker are going to be undergoing step 3. It's not step 1, 2, and 3 because one finishes before the next one starts, but because they feed into each other. Things from step 1 will feed into step 2. Step 2 kind of cycles itself until some of those molecules feed into step 3. Eventually, so many molecules undergo step 3 that step 1 and 2 stop because there's nothing to do those reactions. So they run out of fuel essentially. So this, if you understand this is one of the key things I can tell you that will help you understand free radical substitutions. Don't think of them as individual steps where one ends before the next one begins. Think of them as 3 steps that feed into each other but are constantly happening. So we start with step 1, the initiation step. And we call this the initiation step because without this step, neither of the other 2 can happen. During the initiation step, what's going to happen is that UV radiation, UV light, ultraviolet light from sunlight is going to be used to break halogen bonds through homolytic fission. So why is the UV light needed here? UV light in this step is needed because it provides the energy for homolytic fission. Homolytic fission, like any bond breaking, needs energy. UV light is the energy needed by this step. So the UV radiation provides the energy needed for the homolytic fission. Now, if you remember, homolytic fission is the breakage, the even breakage of a bond. So what's going to happen is that the halogen, whether it's F2, Cl2, Br2, or I2, doesn't matter, the diatomic halogen molecule is going to get broken homolytically by ultraviolet light. When that happens, the 2 electrons in the bond will be evenly distributed. One will go to one halogen, the other will go to the other halogen atom. Again, it doesn't matter which halogen we have, it happens the same way to all of them. So we can show that by doing a curved arrow with a half head, because it's 1 electron, starting from the bond to the atom. And what that creates is it's going to create 2 free radicals. So on this side, these are all free radicals. Why? These are free radicals because they have a single unpaired electron. Remember that these are shown in a very specific way. We're only showing what we want to see here, right? All of these are free radicals because they have an unshared electron, so we're showing that unshared electron. But in reality, fluorine, for example, or chlorine or bromine here, it doesn't really matter which one, has 7 valence electrons with the one that's unpaired. We don't show these other 6 because they're lone pairs. They don't really matter. They're not going to react. So we usually only show the one unpaired electron because that's the important one. That's the one that's reacting. Not the other 6. They're there. We should know they're there. But they're not important to the reaction, so we don't really show them. So these free radicals are the reason why this mechanism and this type of reaction exists. The UV radiation in the initiation step is going to break the free radical, or the halogen, molecules homolytically. Each atom of halogen is going to get 1 electron from the bond, creating a pair of free radicals. And again, depending on, these are all each individual initiation steps that depend on which halogen we have. If the halogen in question is chlorine, like what we saw earlier, so if we have this reaction, for example, where the halogen is chlorine, then this initiation step, the second initiation step, will be the one happening. But we can do the exact same reaction with bromine, just doing this step. So that's the initiation step. UV radiation breaks the bond homolytically. Each atom gets one electron to create free radicals. Propagation. This is the chain reaction part of the mechanism. Propagation steps are going to happen when free radicals attack compounds. We discussed this in chapter 14. Free radicals are extremely reactive. They do not want to sit still. They do not want to exist. So they react with everything they see. This leads the free radical, I'm going to use chlorine here as an example, but again, it could be any halogen, to attack any compound they meet. Usually, in the type of reaction we're looking at, that compound is going to be the halogen molecule. Sorry, not the halogen molecule. The alkane molecule. So we're going to have an alkane here, and it could be any alkane. We're using ethane as an example. So the alkane is going to react with the Cl free radical. And I'm shortening here. So the chlorine free radical is going to react with an alkane, in this case ethane. And what's going to happen is that the alkane is going to essentially give up a hydrogen to the free radical. Or more accurately, should I say, the free radical is going to steal a hydrogen from the alkane. Because again, they're extremely reactive. The alkane doesn't really have a choice. So this hydrogen here is going to form a bond that's shown by this dashed line here to the chlorine, in this case, free radical. So that free radicals are used to one unpaired electron, and we're going to show that with a curved half-headed arrow to create the bond. And then in this carbon-hydrogen bond, there are two electrons. One of them is going to be used to create the bond to the chlorine free radical. The other one is going to go to the carbon. So essentially what is happening here is that the free radical is using its reactivity to break the carbon-hydrogen bond homolytically, creating a bond between the hydrogen and the chlorine, which creates our first product, which is the hydrogen halide. In this case, hydrogen chloride. And then it leaves that alkane as an alkane-free radical. So this right here, this CH3CH2 dot, that's an alkane free radical. This is a free radical that's created from the reaction between the chlorine free radical, the halogen free radical, and the alkane. So that's one step of propagation. Now, why do we call propagation a chain reaction? Well, that alkane free radical that is created is not stable. It's super reactive. So it's going to react with the first thing that it sees. And what is the first thing that it sees most likely going to be? Well, another reactant, the chlorine molecule. This is Cl2. And here's where you might be a little confused. This is Cl2. This is chlorine. This is where it's important for you to remember that the three steps, initiation, propagation, and termination, happen at the same time. So why is there chlorine still present? Well, when step one happens, the initiation step happens, step one is only about 10% effective, meaning that only about 10% of those halogen molecules actually get turned into free radicals. The other 90% is still floating around. And so that alkane free radical that we just created can freely react with that halogen molecule. Or in this case, Cl2 chlorine. It could be Br2, F2, Y2. Doesn't really matter. It depends on what our reactants are. When this happens, again, very similar to the first part of propagation, the chlorine-chlorine bond will be broken homolytically. One electron will go to one chlorine. The other one will go to create a bond between the chlorine and the alkane free radical. So the chlorine and the alkane free radical form a bond, one electron from the free radical, one electron from the chlorine bond, and they create our second product, which is the halogen-alkane. But they also create another chlorine free radical, or a halogen free radical. This chlorine free radical or halogen free radical, if we have a different hydrogen, can then go back to that first reaction and keep this cycle going. So the chlorine free radical reacts with alkane, creates alkane free radical and hydrogen chloride or hydrogen halide. Then that alkane free radical reacts with a halogen molecule, which creates halogen alkane and a halogen free radical, which then can go back and then continue the cycle on and on and on. And as long as we have alkane molecules and halogen molecules and we keep making these free radicals, this will keep happening over and over and over again. That's why free radicals create this chain reaction. We call them a chain reaction. Now, this is going to keep happening, and it's going to continue to react with other molecules until something happens that starts to wean out, to eliminate these free radicals. Because this whole reaction involves, or is reliant on, the creation of these free radicals. So the only thing that can stop this propagation reaction is the essentially canceling out, or the making of molecules out of these free radicals. And that's where the termination step comes in. However, before we discuss that, let's talk about some alternatives to this propagation, because this, what we just saw, is the two most common, the main propagation reactions. But you have to realize something. As these propagation reactions happen, we are creating two things. We are creating hydrogen halides, and we're creating halogen alkanes. We're going to focus here on these halogen alkanes, all right? Because these halogen alkanes are organic compounds, meaning, yes, this chlorine free radical that we created is more than likely going to find an alkane. However, as more and more of these reactions happen, the concentration of alkane starts to decrease, whereas the concentration of the halogen alkane starts to increase because it's a product. So we're making more of this and we're using up more of this, meaning that eventually, as these reactions happen, this chlorine free radical that we create at some point might end up being more likely to find its way to a halogen alkane instead of an alkane. And they can still react, because remember, free radicals will react with anything they see. Same is true of this free radical. This free radical could react with this instead of with a chlorine. Or it could even go and react with a alkane instead of the chlorine. As the concentration of the chlorine drops, this is more and more likely to happen. This leads to something that's very annoying in organic chemistry, which are alternative reactions. Reactions that are less likely, so they don't happen as much, but they still happen. Free radical substitution is not ideal for a creation of a specific halogen alkane. You cannot control what free radicals do. So what happens? The propagation step can actually cause several different alternative products to happen, because we get what we call multiple substitution of the alkane. Multiple substitution, it means exactly what it sounds like. Multiple, many, substitution, exchange. So this means that we said, that chlorine free radical, or the halogen free radical, could find its way not to an alkane, but to a halogenal alkane. That was one of the products. Notice, the only difference between an alkane and this halogen alkane is that one of the hydrogens has already been replaced with a chlorine. Well, that's not going to stop this chlorine. That chlorine doesn't care that it's already a chlorine in this halogen alkane. So the exact same reaction can happen. That free radical can steal the hydrogen, create our hydrogen halide, HCl, and it creates a free radical that is a halogenalkane free radical. So this will be a halogenalkane free radical. That halogenalkane free radical can then react with a chlorine, undergo the exact same propagation reaction, and replace that hydrogen that it lost with a chlorine, creating a dihalide or dihalogen. Okay, I didn't run out of space here. Creating a dihalogenalkane. And this is why free radical substitution is not a great reaction to use to create a specific halogen alkane, because you can have these alternative products from multiple substitution. And in reality, the larger the amount of halogen we have, the more likely multiple substitution is going to happen, because the more chlorine we have. So while we would expect the compound that's created here, to be CCCl H, to be chloroethane, we could also create dichloroethane, in this case 1,1-dichloroethane. But that's the thing, this doesn't just end here. This can actually keep happening over and over again. And we could get 1,1,1-trichloroethane by replacing another one of those hydrogens. And that can keep going on and on and on. We could even make 1,1,1, 2,2,2 hexachlorohexane, which is where every single hydrogen gets replaced with chlorine or bromine or iodine. It doesn't really matter what the halogen is. So these are what we call alternative propagation paths. They can lead to multiple substitution of the alkane, where more and more and more of those hydrogens get substituted with the halogen. There is no way to stop this. The halogenal alkanes created in the reaction can have multiple substitution. They can substitute every single hydrogen, as many or as few as chance deems they're going to created. And in reality, we don't get one product. We get a combination, a mixture of all of those products when this reaction happens. And that's one of the bad things about halogenal alkanes. We can try to limit the amount of this happening, but we cannot stop it completely. Finally, we have the termination step. The termination step is the one that ends everything. As propagation happens, the concentration of the reactants are going to decrease. And we're going to get less and less of those alkanes, less and less of those chlorines or halogens. And that's going to lead to more free radicals actually encountering each other. So what happens when two free radicals react with each other? That is the termination step. The termination step is going to happen when a free radical reacts with a free radical to create a molecule. Now, any of those free radicals we saw could react with each other. So there's three different propagation steps here that we can look at. Step termination step. The first, the second, or the third. All of these can happen. In the first instance, the what do we call this? The alkane free radical is going to react with the halogen free radical. Oh, look, let me rewrite that. So the alkane free radical can react with the halogen free radical and create the halogeno alkane. So the free radical react with each other and they create a molecule, in this case a halogeno alkane molecule. And actually, pardon this shouldn't be a chlorine here, this should be a hydrogen. That is a type that needs to be fixed. So that's a hydrogen. Right? So that's one possible termination step. Another possible termination step is when two alkane free radicals meet. Which is possible because remember, these are all these steps are happening at the same time. So an alkane free radical can meet another alkane free radical. And what ends up happening here is that the alkane free radicals are each going to use their one electron to create a bond between carbons, creating a double alkane. Meaning that if the alkane we were using was ethane with 2 carbons, we're going to get butane with 4 carbons. So we're going to get a twice as long alkane out of this possible termination step. And the last one is when two halogen alkane free radicals, when two halogen free radicals react with each other, in which case they just make the halogen molecule. And they just create our regular hydrogen molecule, which is a reactant. So this is going to create what we call a product, because halogen alkane is a product. Whereas this termination step creates a minor product, a product that is not intended, but could be a minor or byproduct of the reaction. And then this last one actually recreates a reactant. So the creation of halogen alkanes through free radical substitution is very hectic. We can get a lot of different minor products and side reactions because essentially halogen alkanes can be created in multiple substitutions where we add more and more and more halogens to them. So what are the ways in which we can limit this, right? So how can we make sure we get single substituted alkanes out of this? So to get or to minimize the creation of multiple substitutions, to minimize multiple substitutions, we can do two things. We can limit the concentration of the halogen, meaning use low concentrations of the halogen, or whatever X2, we'll call it X, that could be chlorine, fluorine, bromine, or iodine. That's the first way in which we can minimize multiple substitutions. The second way is to use an excess of the alkane. Both of these are going to do the same thing, and that would mean a high concentration of the alkane. What this does is that it makes sure that your free radical for your halogen finds an alkane, because we have a high concentration of these and a low concentration of these. Meaning that the first thing this halogen, and I forgot the A here, this halogen free radical is going to be likely to find is an alkane, and it minimizes the chances that it will find the halogen alkane products. So that's just one way of minimizing. Now, can we absolutely make this chance zero? No. And that's why these reactions are usually not used for specific creations of halogen alkanes. This is mostly just something that happens as a byproduct. For example, if you leave your water bottle out in the sun, your water has chlorine in it, The sun has UV radiation. This could happen with the plastic of your water bottle. This is why they tell you not to leave water bottles, especially disposable water bottles, out in the sun. But that is how free radical substitution works. That's it. That is it for section 15.2 and the reactions of alkanes. And that's pretty much it for alkanes in general. Like I said, they're not very reactive because they're nonpolar. There's only two reactions that are undergoes: combustion and free radical substitution. I will see you all in the next video to start discussing the reactions of a different hydrocarbon, which are the alkenes.